So I'm here with the first sample assessment material for Foundation Physics 2. And there's your list of equations. So there's not many because it's a foundation. Straight in for first question then. Select the right words to fill in the box. So because it is a large mass main sequence, it's got to be a supergiant. And then your supernova, and then your neutron star. Forces, gravity is equal to gas pressure, so the forces are balanced in a main sequence star. Everyone's happy there. Then we've got to put, this is actually question 2 now, it's going on to radioactivity, and we're going to use the dice to represent radioactive decay. Put them in order, so it's going to be B, D, E, C, F, A. When you read through that, that's going to make sense. And then you're given a list of numbers there. That's going to have to be graphed, or at least you've got the remaining to graph. So how many marks available? So 3 marks. You're going to get 2 marks for the plot in, and then 1 mark for the curve, a nice decay curve. And then brings us down to use the graph to determine the half-life. Well, to do that, you need to see that it starts at 400, and then it drops to 200, because that's half. So half of 400 is 200. And then I bring it back down. It's around about 3.8, but that's going to depend on your curve. And then the experiment was repeated to 20-sided dice. How does this affect the half-life? Well, you're going to have a longer half-life because the probability is lower. Think about rolling one, choosing a number 1 on a 6-sided dice. The chance of getting a 1 is 1 in 6. Well, if you pick a 1 on a 20-sided dice, the chance now is 1 in 20. So it's going to take a lot longer for that 1 to come out if you keep rolling a 20-sided dice. Explain why the data from each group was added together. You're going to increase the sample size if you add loads of groups together, and that's going to reduce the number of errors, reduce the number of anomalies. That brings us then to question 3. So there's a little bit of information that you may have to pick out here. So the weight of a body is measured in kilograms. Well, that's incorrect because the weight is measured in newtons. Kilograms is a measurement of mass. The mass of a body is much lower on the moon. Well, the mass is going to stay the same because mass is the amount of stuff in an object. So your mass doesn't change. Weight is going to change because it's going to depend on the gravitational field strength. The inertia of a body. Now, inertia is to do with Newton's first law. So Newton's first law, an object will remain at rest or in uniform motion in a straight line unless acted upon by external force. That's going to be throughout the universe. That's a universal law. So it doesn't matter what planet I'm on. Inertia is always the same. Gravitational force of 2 kilograms on a body on the moon. And we're told there that the moon's gravitational field strength is 1.6. So I can see weight equals mg, so mass times gravity. Mass 2 times gravity, 1.6, is going to give me 3.2, so that's correct as well. What's the force acting up? It's going to be air resistance for 1 mark. Then it says, calculate the resultant force. So everyone wants to do F equals ma here, but a resultant force is just one take away the other. So think about this now. If I got 0.2 coming down, okay, what is going up, and then what's the resultant force? So it's like this arrow, take away this arrow, and how much force is left. Think of it as a tug-of-war race. I've got this amount of people this side, this amount of people this side. By how many is it beneficial on the tug-of-war team? So you would say 0.2 minus 0.04, and that's the resultant pull then, the resultant force. So resultant force is just one minus the other. Then it comes on to using equations. Now you can calculate the acceleration by using your force and then your mass, which was given to you earlier. Because people wonder where I got 0.02 from. I get the 0.02 from the question. So just remember all this is part of the same question. Describe and explain. Sorry, I hit the wrong button. Am I still recording? Yes. I just drew a line there. So let me just undo that. Describe and explain how the acceleration of cake changes over the next few seconds of the journey. So the acceleration is going to decrease. It's still going to be speeding up, but at a slower rate. So we say that the acceleration decreases as air resistance increases. So it's gradually getting faster, but not as fast as it started out. So initially, when you drop the case, the acceleration is massive. But then just remember now, acceleration is the speeding up of something. So you can have a big acceleration and a small acceleration. It still means the speeding up. So the acceleration is decreasing there. And then what's the upward force when it's terminal velocity? So when this is at terminal velocity, downward force is going to be the same because the mass of the case is the same. Gravity is the same. So this is always going to be the same. But when it's terminal velocity, it means that there's no acceleration. It's just a terminal speed. Therefore, that is going to be 0.20 up there. So the arrows are going to be balanced. Thank you, sir.
Yes, half of them will be the half.
Bro. On to question 4 then, which was a 6 marker. Our solar system consists of the sun and blah, blah, blah. So what this question for 6 mark wants, it just wants you to describe our solar system. What's in there? So get the order of the planets in, talk about which one's a gas, which one's a rock, talk about temperatures. So there's generally, the further away a planet is from the sun, the colder it's going to be, apart from a few exceptions, like Venus is the exception to the rule there. Orbit time, generally the longer, well, it's not even generally this time, the further that they are from the sun, the longer they're going to take to orbit the sun. Number of moons, generally the bigger planets have more moons, and again an exception to the rule there is Earth and Mars, because Mars is smaller and it has 2 moons, and Earth is bigger and it's just got the 1 moon. And then we can talk about comets, asteroids, satellites. So moon is a natural satellite, but we've also got man-made satellites up in the up in orbit as well. And you could even mention dwarf planets and things like that, because it's all part of our solar system. Question 5 then. A lot of information here. Again, I would tend to head to, I know this is going to be 2 for 2 marks. I need 2 of these right. So I'm going to head over and then read back. So there are 99 neutrons in the nucleus of technetium-99. Well, that's not true, because technetium-99 means there's protons and neutrons. It's almost like saying I got a class of 99 full of boys and girls, and then that's saying like 99 are just boys or girls. And that's going to be wrong, isn't it? Because you've got to have a mixture of both. So there's going to be, in that 99, you're going to have a number of protons and a number of neutrons. So you can't have 99 neutrons there, because that's just going to max out, isn't it? So that's wrong. There are 43 protons in the nucleus of technetium-99. How do I know that? Because it's number 43. So that's going to be correct. There are 43 neutrons. Well, we've just talked about class size. So if I got 99 kids in a class and 43 of them are boys, this is saying now that there's got to be 43 girls. Well, that's not right, because 99 minus 43 is something else. So that's wrong. Technetium-99 is found in the Earth's crust. Yes, that's true, because it says there, blah, 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 and you can have a read through just to make sure. It's not, found in the Earth's crust, because it's man-made, look. Technetium was discovered by Mendeleev. No, he predicted it. So he didn't discover it. State why the nucleus of technetium is unstable. Well, there's an imbalance between the number of protons and neutrons, okay? There's way too many neutrons for protons. Usually, there's going to be around about the same number of protons and neutrons. But in these radioactive elements, there's way more neutrons. There's your alpha, 2 protons, 2 neutrons. We can also say it's a helium nucleus, and gamma rays a high-energy EM wave. Last bit of the question then. It's got 6 hours half-life, so it's got a short half-life. That's why it's suitable as a tracer. Now, a tracer is something you would either ingest or get injected into you to track the journey of something, whether it's your digestive system or it's injected into your blood, maybe to track the journey of your heart or your circulatory system. So we want something with a short half-life, because we don't want it to be there for years, do we? We want something that's low ionizing, which is going to be gamma. It's the lowest ionizing. In fact, there's no charge to it at all. If we used alpha, it's going to strip electrons. If we used beta, it's going to strip protons from your cells. So we need to use something that's low ionizing, but also high penetrating as well, because you want to track it. If you was to ingest alpha, first of all, it's going to do some damage because it's highly ionizing, but then you won't be able to track it anyway because it's stopped by skin, because your skin's going to block it. So it's just going to be inside you, taking the journey of whatever, and you're not going to be able to track it. So always go for gamma for a tracer, always go for a short half-life. And then the last couple of pages here. So question 6, we're on to work done now and energy. So work done is just energy. So we've got 20 joules, which is the unit for energy, 0.5 meters, which is your distance. 20 over 0.5 is going to give you 40. When work is down, the box and transfer to it, what type of energy does it have when it's on the shelf? It's going to be gravitational or gravity. And then when you knock it off, it's going to be movement, kinetic. So we just need to remind ourselves from year 10, English kids hate learning GCSE. Electrical, kinetic, heat, also called thermal, light, gravitational, chemical, sound, and elastic, or elastical. And then question 7 then, a lot of information, lots of information there. And then you've got this, I guess, diagram with your typical stopping distances, which is split into thinking distance plus your braking distance. So stopping distance is thinking distance plus your braking distance. So you can see there, 20 miles per hour, it's 6 and 6. At 30, it's 9 and 13.5. At 40, so on and so on. I'm going to skip straight to the questions now to see what's going on. The speed limit of 30 miles per hour always indicates it's always safe to travel at 30 miles per hour in that area. No, because sometimes it's icy, sometimes there's wet roads, sometimes the tyre treads is not good. So it's not always safe to travel at any speed. Cars always have a braking distance of 24 meters at 40 miles per hour. Now, you may look at 40 miles per hour, and you can see that your braking distance is 24 there, and you'd think, yeah, that's right. It says 24 at 40. But again, we've just talked about how it's not always going to be that, because of sometimes it could be icy conditions, sometimes there could be things at work that there's not perfect conditions. So that's going to be wrong. However, traveling twice as fast always doubles the thinking distance. Let's have a look at this. So traveling twice as fast. Well, let's start at 20 miles per hour and double it, and then that's going to double it. So that's always going to double. Okay, so it's going to double from 6 meters to 12 meters, regardless of the conditions. Because if the conditions were worse, maybe this is 8 meters, but then traveling twice as fast is going to take that to 16 meters then. So the relationship there is true. Okay, it's always going to double. And then this one is always going to, the typical minimum overall stopping distance at 15 miles per hour is 53. So it says the typical minimum. It's not saying that it always. Okay? And when we add 21, where are we? 50 miles per hour. 15 to 38, you're going to get 53, I think. Yeah. Hopefully I did that wrong. Explain in practice why actual stopping distances. So we're referring back to these couple now. So your thinking distance can change because if you've had alcohol, or you've taken drugs, or there's distractions in the car, or you could be really tired, or you could be just really, really, really old, and your reaction times are just not going to be as quick as, you know, someone that's not taking drugs, not had a drink, is not distracted, is not tired, and, you know, is quite young for reaction times. Your braking distance then doesn't include any of these, so it's all to do with now weather, road conditions, if it's icy, if it's wet, your type of tread that you've got on your tyres, your brake pad conditions, and whether you're on incline, because if you're going downhill, it's much harder to stop, so therefore it's going to increase your braking distance. Describe the relationship between speed and braking distance. It's going to increase by a factor of 4. It's going to quadruple. So whereas thinking distance doubles, so 20 to 40, 6 to 12, and we can check it again, 30 to 60, 9 to 18. It's on about now your braking distance. So from 20 to 40 is 6 to 24. So 6 times 4 is 24. And then from 30 to 60, 4 times 13.5 should take you around about there. Okay? And then using the pattern shown in the data, calculate the overall stopping distance for 80 miles per hour. Well, it's not giving you 80 miles per hour, so you've just got to double the 40, you break thinking distance, so 12 goes to 24, and then you're going to times that by a factor of 4, so 24 times 4 is going to take you to 80 miles per hour then, because you're doubling 40, yeah? So you double 40 to 80. When you double the speed, your thinking distance also doubles, but your braking distance increases by a factor of 4. And we just said that in C. One more question on the back, I think. Oh, so the answer there is 96 plus 24, which gives us 120. And then these last couple of questions, which was quite a couple of the easier ones on the page, which goes to show, don't assume that it just gets harder throughout. Read every question. So the text suggests that airbags reduce blah, blah, blah. So when an airbag goes off, it increases the time it takes for you to hit your head, I guess. Therefore, it increases the distance. Now, there's a way we can prove this by using speed equals distance over time. But for a foundation paper, we're not going to bother for 2 marks. You increase the distance, you increase the time with airbags. Another safety feature is seatbelts. And then if we want to just slow cars down, we can use speed cameras and speed bumps in areas of built up where you want to make the traffic safe. And this was the paper for foundation, the sample assessment material. I hope this has helped, and have fun.